So,
Hello, everyone. Welcome to our last seminar this semester. Today, we are very happy to have Farzam from University of Washington, and he will tell us about planar graphs of uniform polynomial growth. Thank you, Farzam.
hi everyone. Thanks for coming here today. So I'm going to, as Jin mentioned, I'm going to talk about planar graphs of uniform polynomial growth. So, and like in particular, the behavior of random walks on these graphs. So first, let me define you what does it mean for a graph to be planar and have uniform polynomial growth. So I assume all of you already know what a planar graph is. It's a graph that you can draw on the plane in a way so that no two edges cross each other. And yeah, the graph on the left is planar, while it is well known that the graph on the right isn't. Now I'm going to define uniform volume growth to you, but first I need to define a few other things. So given a graph G and a radius R, we define the ball of radius R around some vertex V of G to be the set of all vertices U that are within distance R of V. And by distance, I mean the shortest path distance. And in this talk, we're interested to see how the volume of this ball grows as a function of R. So let's see some examples. So the first one is the integer line, or like an infinite path. And you can clearly see that the size of the balls in this graph grow linearly in R. And the next one is the two-dimensional grid. And you can also see that the size of these balls grow quadratically in R. So of course you can figure out an exact formula for the size of these balls, but there's also some other way to see these balls grow quadratically, and that is to see that they are contained in a like 2R plus 1 by 2R plus 1 ball, and they also contain an R plus 1 by R plus 1 grid, by ball length grid. And so this technique comes in handy later on. So is of course trivial for this case. So yeah, the last example is the infinite binary tree that has, of course, exponential volume growth. And so now here comes the definition of uniform volume growth. We say a graph has uniform volume growth f of R if every ball of radius R in G has volume f of R up to some multiplicative constant. So yeah, as we saw earlier, the d-dimensional grid has R to the D uniform growth. The infinite tree has 2 to the R uniform growth, which is exponential. And yeah, it should be clear that not all graphs necessarily have uniform volume growth. For instance, you can attach an infinite path to a binary tree. And yeah, for some balls it has linear growth, for some balls it has exponential growth. So yeah, just recall that the title of my talk was planar graphs of uniform polynomial growth. So I've defined to you what that means. So now let's see like what these graphs look like. So in 97, Babai proved that if you have an infinite planar graph, or like any planar graph that is vertex transitive and has uniform volume growth, then the growth should be either linear, quadratic, or exponential. So basically it says that the previous examples that we saw are the only possible cases. And it has also been further conjectured by Kleinberg and Tardosh that the assumption on vertex transitivity is not necessary. So if this conjecture were true, you wouldn't have any planar graph of growth like R cubed, for instance. Yeah, but this conjecture was false, and in 2001, Benjamini and Schramm proved that for any real alpha greater than 1, they were able to construct an infinite planar graph of uniform growth R to the alpha. So yeah, so in general, almost all of these constructions have a sort of fractal-like nature to them. So here's one construction by them. So they give a subdivision rule of these quadrilaterals, and they do as follows. They start with the unit square, they subdivide it into these three quadrilaterals as follows, and they mark this vertex in the middle, and they continue to do so for all the resulting tails, and they go on and on, and after a few steps you get something like that, and this gives you a sequence of finite planar graphs that have uniform polynomial growth. I'm not going to prove to you why it does have polynomial growth, but we'll see a similar proof later on. And they further were able to give out some notion that given a sequence of like finite planar graphs, you could obtain an infinite planar graph that has similar properties. So yeah, I'm not going to give out the exact definition of this, but so basically what they're doing is they're considering the sequence of random rooted graphs Qi and Rho, where Rho is a uniformly random vertex of Qi, and they say like they prove that this sequence of finite planar graphs has a distributional limit in the sense that the limit is a random rooted graph that the local neighborhood of this random root somehow looks like the local neighborhood of these random roots in Qi as I goes to infinity. So for instance, if all of these graphs have uniform polynomial growth, what you end up with is a random rooted graph that has uniform polynomial growth. And what they prove is that as long as your sequences of graphs has bounded degrees, such a sequence has a subsequential limit. Yeah, I forgot to mention that. So if you look at the definition of uniform volume growth, if you plug in r equals 1, it tells you that a ball of radius 1 should have a constant size. So all such graphs should have bounded degrees. So yeah, here's one such construction. And the other related construction is the UIPT, which arises in the study of 2D quantum gravity. So it's defined as the distributional limit of random uniform triangulations of the surface of the two-dimensional sphere, like the surface of the three-dimensional sphere. And so these sequences of graphs don't necessarily have bounded degrees, but they still have like the degree of the root still has some exponential tail. And in 2003, Angelo and Schramm defined them and showed that such this sequence has a limit. It was further proved by Angel that these graphs have volume, the balls of radius r in this graph have volume r to the 4 up to some log factors. So here's some drawing of the UIPT, like after finitely many steps, of course. So what you can see is that like it might look kind of strange to you or beautiful, but so one aspect of it that we're interested in here today is that there are these so-called baby universes in these graphs that there are like these thin branches of mass that like contain a large amount of mass, but you can disconnect them from the rest of the graph by just removing a ball of some very small radius. So now Benjamini and Papasoglou asked this question that is this should this be the case for any planar graph of polynomial growth degree greater than 2? So more precisely, like they ask whether there is a graph there is a planar graph of uniform growth greater than uniform polynomial growth greater than 2, in which the complements of our balls are connected. So that was certainly not the case for the UIPT that we saw earlier. And note that if alpha equals 2, like this, the answer to this problem is trivial because, like in the two-dimensional grid, you already have that the complements of balls are connected. So basically, this sort of strange behavior happens when the growth dimension of the balls disagrees with the topological dimension of your graph. And we answer this problem positively. And for any alpha greater than 2, we show that there exists a unimodular planar graph of uniform growth R to the alpha, in which the complements of all balls are connected. I haven't defined what unimodular means, but for the sake of this talk, you can just consider them as like Benjamini and Schramm limits of sequences of finite planar graphs. And okay, I'm going to describe our construction to you later on, but here's a sneak peek at it. They look like this, and a ball in this graph looks like this, which you can see that, I mean, intuitively you can see why the complement of it is connected because it has no hole inside. And yeah, we can also prove that every ball looks like this. So okay, so far I've told you about these graphs. Next, and their structure. And next, I'm going to talk about random walks and effective resistances in these graphs. And finally, I'll describe our constructions to you. So let's talk about random walks. So suppose a guy is standing somewhere in the one-dimensional grid, and then some monster appears nearby, and he decides to run away from this monster by doing a random walk. And yeah, you can see that after a few steps, this guy gets back to his starting point and gets eaten by the monster. So it turns out that doing a random walk is not the best strategy to do this in the one-dimensional grid. And in fact, like you get in the case of one-dimensional grid, you get back to your starting point almost surely. And so, and we call such a graph recurrent, a graph that, to put it in another way, a random walk revisits its starting point infinitely often. And otherwise, we say G is transient. And note that as long as G is connected, this definition does not depend on the choice of the starting matrix. So let's see some examples. So yeah, as I mentioned earlier, Z is recurrent, so is Z squared. But the three-dimensional grid is not recurrent anymore. So you might ask, like, does this have something to do with planarity? The answer is no, because the infinite binary tree is transient. But now you see there is also some other difference, that the infinite binary tree has exponential volume growth, but the grids have polynomial growth. So you might ask if, like, you have both uniform polynomial growth and planarity, could your graph still be transient? And in fact, all of the previous constructions that I described earlier were recurrent by works of Benjamini and Schramm and Gurovich and Nachmias. Yeah, this includes the Q infinity example that I described and also the UIPT. Yep. So yeah, Benjamini conjectured that this holds for every planar graph of uniform polynomial growth. So it's easy to show that this holds. So it's easy to show that if a graph has growth at most r squared, then it is recurrent, even if it is not planar. And this was even further conjectured to be true for doubling planar graphs. So I'm not going to define what that means, but they're basically a larger family of planar graphs, the generalized uniform polynomial growth. So now you might ask, okay, how would you analyze such a thing in a graph? It looks complicated. So there is an equivalent definition of recurrence. So to define that, first I need to define what effective resistances are. So given a graph G and two vertices U and V in it, we define the effective resistance between U and V to be the energy required to send the unit current from U to V, while assuming that like every edge is a unit resistor. So yeah, in this example, you can see that yeah, by some application of series and parallel laws, you can see that the effective resistance between U and V is 1. Yeah, so to put it another way, you can basically replace the whole graph with this single resistor and yeah, obtain something that behaves the same. So yeah, in general, effective resistances and random walks have like lots of connections together, and it kind of arises because both of them deal with these harmonic functions on the vertices of the graph. But yeah, what we're interested in today is, of course, the relation with recurrence. And by the work of Doyle and Snell, we know that a graph is recurrent if and only if the effective resistance of a vertex to infinity is infinite. And what that means is like you can send the flow from this vertex to infinite distance with a finite amount. And with a if you want to send a flow from a vertex to the infinity, you would require an infinite amount of energy. Yeah, to define it more precisely, you would look at the effective resistance from this vertex to the exterior of a ball of radius r around V, and take the limit as r goes to infinity. And yeah, indeed, you can use this theorem to like prove the recurrence of many examples. Yeah, as far as I know, this is the main tool to prove recurrence or transience. So now you might ask, okay, we know it's related to the effective resistances in these graphs. So how would you bound the effective resistance? So suppose you're interested in the effective resistance between U and V, and you know they're kind of separated with these cut sets SI. And by separated, I mean that if you remove SI from your graph, then they disconnect U and V. Then by work of Nash-Williams, we know that the effective resistance between U and V is lower bounded by the sum of the inverse of the sizes of these sets. It is fairly easy to prove. It basically says that if you want to send a flow from U to V, it has to pass through S1, then S2, and then S3, and so on. And in order to pass through SI, you would need 1/4 size of SI energy. That's like sort of a bottleneck for your flow. And yeah, this gives a way to bound the effective resistance. And okay, and somewhat interestingly, we do have some sort of separators in planar graphs of uniform polynomial growth. So by work of Benjamini and Papasoglou, we know that there's a linear size separator between a ball of radius r and a ball of radius 2r in these graphs. And note that if you didn't have planarity, then this wasn't true. So for instance, in the three-dimensional grid, the best thing that you can hope for is a separator of size r squared. But yeah, you can already see that in these graphs, something like sort of unexpected or strange happens. So let's, okay, but this is not enough to show recurrence of these graphs, because like between a ball of radius 2 to the I and 2 to the I plus 1, you only get a separator of size 2 to the I, and the bound that you get from Nash-Williams is the sum of this geometrically decreasing series, which of course converges. And so it doesn't show you anything. So let's look more closely at these separators in the two-dimensional grid. So you can see that all of these like R by R grids form R by like the boundary of the R by R grids form a separator between like a ball of radius R and ball of radius 2R. And in fact, you have like R many of those separators in the two-dimensional grid. So what the Benjamini and Papasoglou theorem told you was that you only get one of them. And if you could have like R of them, then you're fine, and you could show the recurrence of these graphs. Yeah, you can see that like the sum of, so the bound that you get is up to some constant factor, the sum of these 1 over 2 plus 1 over 3 plus so on, which of course doesn't converge. And some other way to see this is that, so to like break up your flow into these subflows from like the ball of the boundary of the ball of radius 2 to the I to the exterior of the ball of radius 2 to the I plus 1. And we're just noting that if you want to send a flow from infinity, you should yeah go first from go from like the ball of radius 1 to 2, then 2 to 4, and so on. And so it is true that for each of these, you would have a constant lower bound on the effective resistance, just because of what I said earlier, that you have like R separators of size about R, and you get R times 1 over R, which is constant. So yeah, so in the case of the two-dimensional grid, this approach lets you prove recurrence. And one might hope that a similar technique might work for like all such graphs. So if you were able to show that the effective resistance across this annuli in these graphs is constant, then you would obtain the recurrence of these graphs by what I said earlier. But we don't know if it's true or not yet. In fact, James had conjectured that this is true for any such graph. And what we do know by work of Benjamini and Papasoglou is that this is at least 1 over R. But the lower one that we need is a constant that doesn't depend on R. And just before answering this question, let me tell you that if this conjecture were true, it would have resolved Canons conjecture from geometric group theory. Okay, I'm not going to fully define it to you. So it is basically saying that if you have, roughly speaking, if you have a planar graph of uniform polynomial growth that has lots of symmetries in it, then the effective resistance across annuli in this graph is constant. And this is through a work of Bonk and Kleiner. The way that you obtain these planar graphs, I mean. So to put it in some other way, so their objects of the studies are these finite subdivision rules. And So what they propose is that if your set of subdivision rules have like lots of symmetries to them, then you can always draw them on the plane in a way so that all of your tiles remain round, that they don't like become extremely thin or whatever. The aspect ratio remains a constant. And yeah, that's all I'm going to say about them today. They're not going to come up in the rest of the talk. Uh, so unfortunately, we cannot answer Canon's conjecture yet, at least. Uh, but what we can do is we disprove the conjecture of James. So if this is false, it doesn't imply that Canon's conjecture is false, because it's a stronger statement. So yeah, in fact, for any alpha greater than, sorry, it should be alpha greater than 2. For any alpha greater than 2, we can construct a unimodular random graph that in which the effective resistance across annuli is 1 over r to the 1 minus epsilon. So this basically says that the bound that you get from the Benjamini and Papasoglou separators is nearly tight. You can get as close as you want to 1 over r. And yeah, even these graphs are like by construction recurrent by a theorem of Benjamini and Schramm, but still you can't prove the recurrence using this method because like, yeah, the effective resistance across the constant annuli is not bounded, is not lower bounded by a constant. So yeah, so these graphs, as I said, are already recurrent. So this doesn't yet disprove the conjecture of Benjamini, but we can kind of modify our constructions to obtain a transient planar graph of uniform growth R to the alpha for any alpha greater than 2. So yeah. So now let me tell you about our constructions. So by the way, if there are any questions, please interrupt me. And okay, so our constructions are based on tilings of the unit square, to which so we associate this dual graph to them. And yeah, you can see that this graph has like 12 vertices and every 2 tiles that share an edge are adjacent. And the main ingredient of our constructions is this tiling product, which is defined as follows. The tiling product of S times T is defined in the following way, that you replace every tile in S by an appropriately scaled copy of T. And yeah, you can see one such example of this product here. So this is an important definition for the rest of the talk. If it's unclear, please interrupt me. Yeah, so one key observation is that this product is associative, and like A times B times C equals A times B times C. So if you start with this 3x3 grid as your base construction and look at the powers of G, you can see that G squared is a 3 to the 2 by 3 to the 2 square, and G to the 3 is also a 27 by 27 grid. And if you take the limit of Gn as n goes to infinity, you obtain the two-dimensional grid. Now let's look at the more interesting example. So if you take your base construction to be this tiling H, which is defined as follows, and look at the powers of H. So here's H squared, and you can see that it is obtained by replacing every tile in H by a copy of H, and so on. So I claim that these family of graphs have uniform polynomial growth. And so if you take the limits of Hns, you obtain a unimodular random graph that is recurrent. Is not still transient, but it does answer most of the questions that I described earlier. So yeah, you need one more trick to obtain a transient planar graph, but I'll get into that later. So yeah, so let me tell you why these graphs have uniform polynomial growth. So I claim that they have uniform polynomial growth of degree r to the log base 3 of 12. So here are some simple facts that kind of imply this lemma. So the first one is that if you look at a ball of radius about 3 to the n in Hn, you see 12 to the n many vertices. So to prove that, we need two things. First, that the size of Hn is 12 to the n, and the diameter of Hn is also about 3 to the n. And you can see that putting these two things together, you get this. And note that like 12 to the n is 3 to the n 2 log 12 base 3. So why is that true? To see why h to the n has 12 to the n many vertices, you can just simply prove it by induction, while noting that h to the n is obtained by putting together 12 copies of h to the n minus 1. And to see why the diameter is small, you can also view it in the following way, that let's suppose we want to say the distance between these two marked tiles is about 3 to the n. And note that h to the n has like 3 to the n many columns, and in particular the first and the last columns have 3 to the n many tiles in them. So to obtain a path from, say, the top marked vertex to the bottom one, what you can do is to move at most 3 to the n distance to hit the first column, to the left to hit the first column, and then go down at most 3 to the n distance so that you get into some tile that is in the same row as the bottom marked vertex, and then go to the right at most 3 to the n distance to reach that vertex. Yeah, and you can see that the size of this path is at most 3 to the n plus 1. And yeah, you can further see that there are two vertices for which this distance is at least 3 to the n. For instance, the bottom left tile and the top right one. And it is further true that like the distance from the left of h to the n to its right is also about 3 to the n. By left, I mean the tiles that touch the left edge of h to the n. And if you want to get from any such tile to the right to one of the tiles that touch the right boundary, you would need to go through 3 to the n many vertices. And the same is true for going from top to bottom. And now the final claim is that if you, instead of looking at a ball of radius 3 to the n, if you look at a ball of radius 3 to the k for some k smaller than n in Hn, what you see is basically some copy of hk, or to be more precise, a constant many copies of hk. So how do you prove that? So yeah, first we use the associativity of this product to write Hn as a product of h to the n minus k and h to the k. And here's the claim: if suppose you like v lies in one of these copies of hk, and the claim is that if you look at the ball of radius 3 to the k from v, it basically covers that that copy of h to the k and only touches a few adjacent copies. So let's look at some of these balls. So if you start from this bottom left vertex, your ball grows like this. And yeah, you can see that. So here the like thicker lines denote h squared, and the original graph was h cubed. And you can see that this ball like contains one copy of h in h cube and touches like the adjacent copies of uh, these tiles, the adjacent like corresponding tiles in h cube. So here's a larger ball, and you can see that this has like a larger radius, but it also like only touches a few adjacent tiles to the original copy of uh, h cube here. And yeah, here's some other ball that starts from some other vertex, and yeah, you can see a similar behavior appears here. So, so basically what's happening here, and what you can prove is true, is that a ball of radius like 3 to the k only like touches the neighbors of your copy of h to the k in h to the n minus k. So if you can bound the degrees in h to the n minus k, then you are done. Because you only see that many other copies of h to the k. So bounding the degrees in h to the n minus k is equivalent to bounding the degrees to h to the n in general. And yeah, the claim is that the maximum degrees in hn is 6. And why is that true? You can simply prove that by an induction h. And basically, the main thing that you need to be true about h is its symmetry, or more precisely, the fact that the first and the last column in h have like they are symmetric. They have the same number of tiles in them. So yeah, you can see that if you if you go to h squared from h, yeah, so the tiles that corresponded to the right edge, the right like the tiles that touch the right side of edge now like are adjacent to the tiles that touch the left edge of a copy of edge. And so to put it another way, what you can basically prove is that, so note that these HNs, what they look like is they consist of 3 to the n many columns, and in each column you have some tiles of a fixed height. And the claim is that the ratio of the heights of adjacent tiles is at most 2. And yeah, using this symmetry, you can prove this by an induction on n. And if you have that, then then you can see that every tile has like 2 neighbors on the right, 2 neighbors on the left, one on top and one on bottom. And so we get the degree bound, the desired degree bound. Yeah, you can, should be easy to see. So now this already gives you a planar graph of a family of planar graphs of uniform polynomial growth. And yeah, so yeah, as I alluded to earlier, these graphs have this property that the complements of balls in these graphs are all connected. And yeah, more precisely, what you can prove is that the intersection of these balls with every column is just an interval. So yeah, they have no holes in them. And if you take the complement, you see a single connected component in the rest of the graph. Um, yeah, these graphs also satisfy the property that the effective resistance across annualized subconstant. But if you just take the limit of Hn, it is still recurrent. So here's what you should do to get a transient construction. You should just concatenate these copies of HIs together. So yeah, you can see that what I just did. I put a copy of H on the left, then concatenated it to a copy of H squared and H cubed and so on. And the claim is that this graph still has uniform polynomial growth of the same growth rate, and it is transient now. So why is it? Why does it have uniform polynomial growth? The reason for that is pretty simple. So if you look at a ball of small radii, and by that I mean, like, look, if your vertex lies in a copy of h to the k and your radius is much smaller than 3 to the k, then this ball basically doesn't see any other vertex outside h to the k. So you get the polynomial growth bound the same as before. And if your ball is, if your radius is much larger than 3 to the k, if it's 3 to the n, then as like the size of these balls and the diameters and everything are geometrically decreasing, you would be seeing like all copies of h1 up to hn if you're looking at a ball of radius 3 to the n. And because of this geometric, geometrical increasing, and because of this geometric increase in this size, the size of this ball is dominated by what you see in the copy of h to the n. So again, it just gets down to the analysis in just a single copy of h to the n, which we have already done. So, okay, now let me tell you. So I hope now you believe me that this graph has uniform polynomial growth, but now let me tell you why is it transient. So in order to prove transience, what you need to do is to compute the effective resistance from, say, a tile on the left to the infinity, and say uh, it has like finite effective resistance. And the only tools that you need are the series law and the parallel law. Yeah, but let's do it more precisely. So what I do is I break this flow into the following subflows. That in the ith part, I send a uniform flow from the left of the copy of h to the I to its right. And by left, I mean the tiles that touch the left edge, same as before, and same goes for the right. And you can see that if you compose these flows together, you obtain a flow from the left of like h1 to infinity. So yeah. So yeah, I go from left of h1 to its right, then join the left of h2 and go from left of h2 to its right, and so on. And the claim is that so yeah. So let's call this effective resistance of that sends of the flow, the energy of the flow that sends a uniform flow from the left of hi to its right by rho of hi. And yeah, by what I just said earlier, you can bound the effective resistance to infinity by the sum of these rho of hi's. And the claim is that this is a geometric series. And rho of hi like decays geometrically as I goes to infinity. And to see, yeah, of course, if that is true, then you get a finite sum that tells you that T infinity is transient. To see why that is true, this basically follows by an induction on n. And just noting that in h to the n, you replace every tile with a copy of h to the n minus 1. And it essentially gets down to analyzing this circuit that is in which every edge is obtained by a copy of h to the n minus 1, or more precisely, it has resistance rho of h to the n minus 1. And yeah, by some applications of series and parallel laws, you obtain that the effective resistance of Hn here, I mean, rho of Hn here is 5/6 times rho of h to the n minus 1. And just note that if we didn't have, so the way we are saving here is just because of this middle column that has, since if it had just 3 copies of h to the n minus 1, same as the other columns, then what you would get was 1/3 times 1 plus 1 plus 1, which is 1. And you will get anything sub-constant. You're basically saving because of this middle column. And yeah, so this just proves that to you. And yeah, you can make this more precise, but yeah, that is basically the main idea. So what I've described to you until now gives you a family of like planar graphs that have polynomial growth log base 3 of 12 that answer all those previous questions. But the way that you get arbitrary degrees of growth is also pretty simple. So instead of working with this tiling H as your base tiling, you can instead work with a tiling that has more tiles in the middle column, or more generally, you can have, instead of like working a 3x3 tiling, you can work with tiling of larger side lenses. And if you do a mix of these ideas, you can get arbitrary degrees of growth for any degree greater than 2. Yep. So something that I didn't cover in this talk, but I want to just mention is that so we also answer some other interesting question about these random walks on these graphs, and that is about the speed of the random walk in these graphs. So the speed of random walk is defined as the expected distance that you take after taking like t many steps in the random walk. And so it has been proven by James previously that so the speed is upper bounded by t to the 1/max of 2 and d minus 1. And you have a lower bound of t to the 1 minus d. I forgot to mention it here. And basically the question is which one of these is tight. And need we show that this upper bound is tight, almost tight at least. So for any epsilon greater than 0, we can get the speed of the random walk to be as close to this as possible. The way you prove this is also relatively simple. So in addition to what I just said earlier, the only thing that you need is this relation between the heating times and effective resistances. I mean, more precisely, there is a nice formula that relates commute times and effective resistances, and then you can just use unimodularity to get from the bound on the heating times to the bound on the speed of the random walk. Yeah, that's all I'm going to say about it. So let's just wrap it up now. So I told you that for any alpha greater than 2, we can construct a transient planar graph of uniform growth R to the alpha. And furthermore, a unimodular random graph in which the complements of all bars are connected. He has subconstant effective resistance across annuli, and the speed of the random walk is about 1 over d minus 1. And so let me mention some open problems. So Canon's conjecture still remains wide open. And in fact, we tried for a few months to see if we can disprove it using similar ideas and techniques that I just described to you. And okay, I'm not sure that it can't be done, but it seemed like the constructions that you obtain from these ideas don't have enough symmetries in order to satisfy the requirements of this conjecture. But maybe okay, we haven't proved that they don't have these sort of symmetries, and it might be that you could modify these ideas to get something that works. At least our constructions tell you that if you want to prove Canon's conjecture, you need to use these symmetries. You can't just rely on the fact that they have uniform polynomial growth. And another question that is kind of interesting to me is, can you get rid of this epsilon factor in the effective resistance and the speed bounds? And so this is interesting for a couple of reasons. So the first one is that, okay, I mean, I don't have a proof for it, but I think the reason that your constructions don't have enough symmetries in the context of Canon's conjecture are kind of related to the reason that you have this factor of additive factor of epsilon in your bounds. If you can get rid of that, maybe your construction is symmetric enough. But my guess is that you can't do that. It's just a guess. I don't have any reason for it. Just that I tried and I couldn't do it. And in particular, just because of this factor of epsilon, all of these random walks in these graphs are subdiffusive. We know the random walks are at most diffusive in these graphs, but could you have such a graph that in which the random walk is diffusive? We don't have an answer to this question, and this was also a question that was asked by Benjamini and Papasoglou. And finally, can you find any other applications for these ideas? Maybe like they resolve some other open problem as well. In general, seems like our constructions have some unexpected spectral properties, and I wouldn't be surprised if they resolve some other problem that is related to I don't know, effective resistances, or something or the eigenvalues of the matrices or whatever, I don't know. So as one application of these ideas, in an upcoming paper with James, we sort of generalize these constructions to some higher dimensional ones. And what we do is we sort of show that the higher dimensional generalizations of the Benjamini and Papasoglou theorem and separator theorem doesn't hold for d-dimensional sphere graphs. And yeah, that's it. Any questions?